So this is lesson 4, the last lesson of Unit 7. So we're still solving exponentials, but this time we're solving word problems. So we have to remember how to write an exponential function. This says suppose there's 25 bacteria in a petri dish, and the number of bacteria doubles every hour. So let's fill in the table. At time 0, the starting amount of bacteria is 25. If you double every hour, that means you're multiplying by 2. So 25 times 2 is 50. That's how many bacteria you have after 1 hour. After 2 hours, I double the 50 to be 100 bacteria. And after 3 hours, there's going to be 200 bacteria. So we write a function for the number of bacteria after t hours. So I have y equals, now remember, I start with the starting amount of bacteria. The number in the parentheses is your growth rate, or doubling, to the t power. Now, so let's find the number of bacteria after 6 hours. So 25 times 2 to the 6, and we're going to type that right into decimals. And it tells me after 6 hours, I will have 1,600 bacteria. That should be reviewed, the first part here. Now let's spend a little bit of time working with a Desmos or a calculator and solving these exponentials. So here's our equation that we wrote, 25 times 2 to the t. It says use a graphing calculator or Desmos to graph that function. So let's take our time here. Y equals, now when I graph in Desmos, I can't use t, I have to use the value of x. So here's the equation. Now, unless I pull way down, I can't see the y-intercept or anything, which is what the next couple questions are asking me about. What does the x-axis represent? Well, the x-axis, that's your exponent up here, and my exponent was t, which is time. So my x-axis represents time. We want to adjust our Windows setting. Well, time, I can't have negative time, so maybe let's make the window, I'll show you how to change this in a minute, be from 0 to, I don't know, 20. We can always make it bigger, but let's start from 0 to 20. At least we'll see a little bit more. So on Desmos, to change your window, you hit top right corner here, you hit the wrench, and you should see x-axis. So I'm going to change that number to 0 and the right number to 20. And that's just what you're counting by, is 1s, 2s, 5s. Let's go by 5s. Okay? So at least, where's my graph here? Oh, here we are. There we go. If I started at 0, and I went out to 20. That's why I couldn't see it. Now, the thing is, I can't see the other part of my graph, so let's talk about the y's. The y-axis represents the number of bacteria. And we know at least to 6, if we start with 25 bacteria, right? I'm going to start at 0 though, but we know our y-intercept is 25. But I know that even at time 3, I got 200 bacteria. At 6 hours, I had 1,600 bacteria. So, I don't know, let's make it like 2,000 maybe. We're just going to go higher. So we'll make our window go up to 2,000. I'm just guessing. I don't know what's perfect for sure. But I'm going to change this. So remember, we had 0 to 20 here. And the y-axis, I'm going to go 0 to 2,000. Now in Desmos, you can't put the commas. And let's go by 50s. So if I look at the graph, see how that's a little bit nicer to see. Right? And I can always pull it out a little bit, because then look, I can see my y-intercept there at 0, 25. All right, now, it says use the table in your graphing calculator to determine between, or in Desmos, to determine between which 2 hours the bacteria count will be 500,000. Now I'm going to show you 2 ways to do this. First of all, I'll show you on the table. So you'd have to make a table, and you're going to go through here and type in numbers until you see 500,000 on your table. So it's going to take a little bit of time. Haven't gotten it yet. I'm still at 10,000, or 12,000, 25,000, 204,000, 409, looks like I'm getting close, 800. So if I type all those numbers in my table, I see that, and I'm gonna make a little table here. It's hard to see on Desmos, but I had this table with x and y's, and at x equals 14, I had 409,600, and at 15, I had this many bacteria. So somewhere in between those, between 14 and 15 hours, I got to 500,000. That's not hard, but there's a faster way if I'm using Desmos that I can use. So let me get rid of the table here. I'll just rewrite it. Y equals. All right. Now if I have my table, I want to know where I equal 500,000. And the number of bacteria we said up above in part C, the number of bacteria was our Y value. So if I type in the line underneath Y equals 500,000, I just have to zoom out a little bit. But if I zoom out, keep going, you know there's a lot there, it's okay. It's 50,000, going 500,000, it's hard to tell, but that's where they intersect. Notice the exponent, the time is at 14.288. That's in between 14 and 15. So you can always graph it and find the intersection to find the time. So that's between 14 and 15 hours. Now, write an equation to find it exactly. So we're actually going to find that 14.288. Our equation here, well, this is what we know about the bacteria. And we want to know when does it equal 500,000. We learned how to do this in lesson 3. We're going to isolate the 2 to the t. Oops, that's not what I wanted to do. We're going to isolate the 2 to the t and then use the logarithm. So divide by 25. I have 2 to the t equals, now 500,000, I'm going to go in line here, 500,000 divided by 25 equals 20,000. And then I take the log of both sides. So I'm going to bring my variable in front, log of 2, and divide by log of 2. So when I divide log of 20,000 divided by log of 2, do it here, log of 20,000 I got 14.288, which is the same thing I found for my intersection. So it's going to take 14.288 hours until there are 500,000 bacteria. That's not really even that long. That's like if you start at midnight counting bacteria, that would be 2 o'clock in the afternoon. All right, flip your paper over. One more problem. Very similar in structure. We're going to look at the graph, we're going to look at the table. So I'm going to clear out Desmos here. And I'm going to make my grid. Just going to start back at the main. All right. Just start over. All right, that's how we start. So let's see. Suppose you have a patient that's taking a medicine or a drug that reaches peak level at 300 milligrams in your bloodstream. And then you know when you take a medicine like ibuprofen or Tylenol, it wears off after a while. So this drug is eliminated or wears off at a rate of 20% per hour. So let's review percent decrease from the previous unit, from unit 6. So if I have a function of time, I know that I start with 300 milligrams of the drug. Now, if I'm decreasing by 20%, remember percent decrease was 1 minus the percent written as a decimal. Remember, I could write that also as 300 times 0.8 to the t. That's the same expression, but that's telling me that the amount in my bloodstream is going down. So let's fill out this table here. If I know the model, 300 times 0.8 to the x. And I make my table. I start at 300, and I need to know the values out to 5. Okay, so go ahead and hit pause. Work on typing this table onto your paper. All right, what this table tells me is that, like, after 1 hour, 80% of the drug that's still there, there's still 240 milligrams left. And then after 2 hours, there's still 192 milligrams left of the medicine. Okay, so I take this equation and let's answer some questions about it. What does the x-axis represent? Well, the x-axis, again, is our exponent, which is time. So that's the number of hours that the medicine is in your bloodstream. So let's see, at least with my table here, I was going from 0 to 5. Let's make it to 20 again. Let's just make it go to 20. That way I'm kind of covering a lot of stuff. What does the y-axis represent? Well, remember, this is y equals. And the y column of my table was telling me the amount of medicine in my blood. Now, if I started at 300, it's going down from there. So I really only need to make my table go from 0 to 300 because I can't be higher than 300. That's how much you started with. And I can't have a negative amount of medicine. So that's going to be my window setting. So let's go ahead and type that in to Desmos. I already have the equation. Let's make our table. So we go from 0 to 20. And again, we can go by 1s or 5s, it doesn't matter. And then 0 up to 300. And maybe I'll go here by 50s. All right, there's my graph. Look, you see it's a decreasing exponential function. Looks pretty good. So the next part that it's asking me is determine how long it'll be until there's less than 10 milligrams of medicine in your blood. So just like before, I'm just going to keep going through my table here and typing in numbers until I get down to 10 milligrams on the right. So I'm at 32 right now, 25, we're getting there, 13, there's 10 point, but it's not less than. So it looks like it's going to take 16 hours until I get less than 10 milligrams. So between 15 and 16 hours. Okay. Remember, the other way that I could have done this is to go into Desmos and type y equals, that's the amount of medicine, equals 10. I look here then on my screen, you see on the bottom there's that intersection. I can click where they intersect. Oops, I can't do that with the table here, hold on. I'd have to retype this. There we go. I can see where they intersect here, which is 15.2, which is between 15 and 16 hours. All right, so let's practice solving this by hand. All right, so I want to know, when does this equation, 300 times 0.8 to the t, get me to 10 milligrams? Well, I start by isolating the 0.8 to the t. And I'm going to do that by dividing by 300. All right, now, it's not going to give me a nice decimal, but 10 over 300 is at least 1 over 30. So I can at least simplify the fraction that way. And then I'm going to take the log of both sides. The log, when I do that, I bring the 10t out in front. And then divide by log of 0.8. And I will have t equals, I'm going to type in log of 1 over 30 divided by log of 0.8. So I'll take log of 1 over 30 divided by log of 0.8. I got 15.242, which is what we found before with our intersection. So if you took this medicine at the beginning of the day, 300 milligrams, it would take 15 hours until there was less than 10 milligrams left in your blood. All right, try to practice, and then you're ready for your test review.